This is the graph of the Weierstrass function. Initially, it looks like a cosine wave, but as b increases, the graph becomes increasingly jagged. It's perhaps best known for being the first published example of a function that is continuous everywhere, but differentiable nowhere. So it never has a defined gradient. Prior to its publication, the general belief was that continuous functions have well-defined derivatives. For example, take the x-squared graph. At any point on this graph, you can draw a tangent so it has a gradient at every point. Differentiating the function also gives a formula for the gradient with a definitive output for a value of x. But once the Weierstrass function was published, it directly proved the concept that all continuous functions have derivatives to be wrong by contradiction. At any point, it is continuous, but it never has a derivative. So why is this the case? The Weierstrass function is defined as follows. So the output to some value x1 is an infinite sum of these values. Note that a must be between 0 and 1, otherwise the infinite sum will not converge. For example, if a equals 3, this part of the sum is 1 plus 3 plus 9, which tends to infinity, so the function is not defined. Now, let's differentiate the function. The derivative of cos kx is minus k times sine kx. So we take out the constants b to the power of n and pi, and cos changes to minus sine. Rearranging gives this. Now, notice this part of the derivative. It's a sum to infinity of a times b to the power of n. But if ab is greater than 1, the infinite sum will never converge. For example, if ab is 2, the sum is 1 plus 2 plus 4 and so on. Therefore, if a times b is greater than 1, the derivative does not exist at any point. We can also explain it graphically. First, let's look at the definition of a derivative. At any point x on a curve, you can draw a line which intersects the curve again. The gradient is the difference in y over the difference in x. As the difference h tends towards 0, the gradient of the line will be the exact gradient at the point x. That gives this formula for the derivative of any function. But now, look at the Weierstrass function. As we zoom in, more and more peaks keep appearing, so the graph never settles. Going back to the formula, even as h tends towards 0, we can't get the gradient because the graph keeps jumping around. Therefore, there is no defined gradient. To this day, the Weierstrass function is perhaps the best-known example of a function that is always continuous, but never differentiable. It served as the first counterexample to a long-believed rule, perfectly exemplifying how quickly our understanding of mathematics can change with just a single idea.